Greenstat Group, as well as several hydrogen projects in India and Sri Lanka. Over to you, Oda.
Thank you, Sibi, for a very nice introduction. Thank HVL for also a very good introduction to hydrogen, and I'll try and cover a big topic very concisely in this session on the techno-commercial aspects of green hydrogen. I work for Greenstat. I'm based in Norway, but as mentioned, I work very closely with our team in India and Sri Lanka. And Greenstat is a green hydrogen company. We also work with solar and wind. But today I'll focus on our project development cycle in the green hydrogen sphere. Talk a little bit about designing an electrolysis plant and sizing the plant, and also a little introduction to the costs and some examples from our project portfolio. So let's get right to the big topic, and how we get from an idea to actually producing green hydrogen. This is the Greenstat model, and that's what we follow when we work with green hydrogen. We try to identify potential projects very early based on market mapping and involvement with communities and our partners. And then we work very systematically to reduce risk associated with the project, with analysis, commercial development. We work very closely with technology suppliers and investment partners, as well as the local communities and the political leadership. So as we go through and mature the project, the value of the project is increased, and once we get to the final investment decision, we aim to farm down our ownership actually, and let other partners in on the investment as well. So this is the model that we work with, and we have a project development cycle, which is divided in different stages that we go through. And obviously the first stage is the feasibility study that we can do for our own projects, and we can do for others, depending on the project. So each project phase is ended with a decision gate, essentially, where we try to identify the highest risk and decide on whether to move on further. So that's a brief intro, and then let's go right into what we require to build a green hydrogen project. And in the simplest sort of form, all we need is water, renewable energy, an electrolyzer, and a hydrogen consumer. And the fundamentals need to be in place. There's no way around it. We have to look at our renewable energy availability. That we'll get back to that a little bit later. The type of energy source that we have. We have to look at our water availability and quality. There's no way around it. If you're going to produce hydrogen through electrolysis, you're going to need water and electricity. And then we have to look at the different options for electrolysis. So that's the technology, the efficiency that we get, what kind of maturity the technology has, the reliability, and what production rate we're requiring. And finally, just to start, we have to know our end markets. What's their offtake profile? What sort of specifications do they have for the gas? Are they going to need it compressed, liquefied, in the form of ammonia, and other hydrogen carriers, as we've been through today? And that's kind of the basics, but there are a lot of other design elements that we need to think about once we start to mature the project. And that's the balance of plants generally, but that includes the gas handling, the purification, the drying. If we're going to compress the hydrogen, what sort of energy cost will that have? How much storage do we need? Do we need a buffer storage? What are the safety aspects of storing the hydrogen compressed? Are there any constraints in terms of the area that we're storing it in? If we are distributing the hydrogen, how far is it going to be distributed? What will be the energy cost of transporting the hydrogen? And we also have to look into the byproducts. So that's oxygen and heat. Oxygen is always produced as a byproduct from electrolysis, and selling that to someone who needs oxygen is a good way to improve the economics of the project. So we try to look into that, but it's obviously not always trivial to sell oxygen just because you produce hydrogen. So and obviously heat is a small byproduct, but it's also a potential useful energy source that can be used elsewhere and sold as a part of the project. So this is just an overview, and I want to spend some time on this because it's often not discussed, because we often think of the hydrogen plant as only an electrolyzer, and I want to illustrate how many components are actually required to get a functional plant. So in addition to the electrolyzer system, we have the civil works, the buildings, lights, access roads, offices, and we need to balance the plant with water, nitrogen, compressors, storage, and we often have an overarching control system in the form of an energy management system that might also wrap up the renewable energy production if we're doing a sort of integrated project. And inside the electrolyzer system, we have the electrolyzer itself, which includes the stack, the balance of the stack, gas liquid separators and connectors. We have power electronics like rectifiers, transformers, and we have the balance of the system with gas and water purification, like I mentioned, and the electrolyzer PLC or control system. So an industrial plant might actually have several stacks or electrolyzer units, or even full systems, because there are some benefits to having several smaller systems instead of one large one, especially if you're scaling up your production from a small initial project phase until full-scale production will come in later. So that's why you often can see phase-wise build out, but that's obviously more costly because you have to balance the plant even when it's small. So important to keep in mind and important to understand if you're designing a hydrogen plant. So I mentioned power availability, and especially in countries like India and Sri Lanka, I want to illustrate the difference between a project there versus a project in Norway. In Norway, we generally have renewable energy available through the grid. We have massive amounts of hydropower, which gives us renewable energy availability of 100%, essentially. That's more complicated than that, but that's what we operate with. However, if you're producing hydrogen from solar or wind or a hybrid plant, you have to consider what your availability will be, and that's going to dictate what your required electrolyzer capacity will be, essentially. Because when you don't have any power, you don't produce. So for solar, that's basically when the sun goes down until it comes back up again. For wind, it will vary greatly throughout the day, and if you combine the two, you might improve your availability, but it's a little bit more unpredictable. So this is going to be your main input for dimensioning your electrolyzer system, essentially. So just some rules of thumb. You need 2.5 megawatt of electrolyzer to produce 1 ton per day of hydrogen if you have 100% renewable energy availability. So if you're going to produce 10 tons per day of hydrogen and you have 100% renewable energy availability, you need 25 megawatts of electrolyzer. in general. However, if you have only 25% of available renewable energy during the day, you're going to times that by 4. So essentially, your oversize factor is 1 divided by 25%, which is 4. And then you get 100 megawatt of electrolysis. And you need to store the excess. If you're going to supply hydrogen at a constant flow rate, you're going to have to store your hydrogen, actually 8 tons of the hydrogen, in order to supply at a constant rate. So this is a very simple calculation to estimate the size of your system. Actually, the optimal solution in terms of cost might be a lot more complex. So I'm not going to go into all the details, but that's a lot of our time is spent on trying to dimension the renewable energy and the hydrogen production versus the demand, and how much you can fail on delivery in order to get your optimal cost of hydrogen. And LCOH, I'll just spend some time with that as well, because in a sea of acronyms, this might be one of the most important ones. LCOH stands for levelized cost of hydrogen, and it's a way of measuring the cost of producing hydrogen over the entire life cycle of the project, from the initial stage of the production point to where it's used. So it takes into account all the expenses involved, the cost of setting up and operating the equipment, and the cost of the resources like electricity and water, and all the maintenance costs as well. So it's a way to give an understanding of the expenses involved in producing the hydrogen, and it's giving us the ability to compare with the cost of other production methods. So here we see in the figure here that the LCOH will vary according to the electricity price, obviously, because it's our main input, and also with the type of electrolyzer that we choose. With currently, well, alkaline might be the cheapest currently. However, there are options to use SOAC, though it's not fully mature, and PEM is quite a bit more expensive. And what is also showing that the cost of these technologies is trending downwards. We are seeing some reduced cost. Well, we will see some reduced cost in the capex side of the equation, which will give us a lower LCOH as we go into 2030, 2040, and 2050. So the last parameters to keep in mind when we're calculating LCOH is the utilization rates. So that's how much of the hydrogen you can sell versus how much you can theoretically produce. And as you increase the utilization rates, it makes sense that you lower your LCOH. So at the beginning of a project, when offtake is uncertain and might be low, you have basically a more expensive LCOH or a lower utilization rate. And then as well, demand increases, we'll see that these LCOH numbers go down as well. And this promise, this $1 per kilo in 1 decade, is something that's been mentioned both in the US and in India as a target for green hydrogen. And I mean, I want to discuss this with you as probably a good target to have. If you think about the fact that green hydrogen is called to replace current uses of fossil hydrogen, so mainly used in fertilizers and oil refining, but it's also a solution where electrification is difficult. So that's steel production, long haul trucking, shipping, aviation, and there is quite a lot of debate on how much green hydrogen will actually be needed. But that's that's more complicated to discuss here. So what we really need to do is to try and compare the cost of green hydrogen compared to the cost of gray hydrogen, and that can vary depending on the location where in the world you are. So in the US and in China, fossil hydrogen might cost like $1.5 per kilo, and in Europe it might be closer to $2.5 per kilo. It depends on the cost of natural gas, and it's not a constant number. So in order to compete with fossil hydrogen, you require about $1 or $2 per kilo of hydrogen. And to achieve this, we actually have to look at two things. We have to look at our capex, and we have to look at our opex. And the reduction in capex will come from innovations in the electrolyzer design, and also improved sort of manufacturing and economies of scale. And this trend might be on its way, but we have to go pretty low in terms of cost per kilowatt. And as the cost of the stack and the electrolyzer decrease, the balance of plant, which I mentioned at the beginning of the presentation, will become basically most of the cost of the hydrogen. So that's the capex side, and then obviously the other half of the equation is the opex, or the operational cost, and that's basically all electricity costs. And you need an electricity cost of about $20 per megawatt hour to reach $1 per kilo of hydrogen in the optimal scenario. So I hope this is clear to you that targeting $1 per kilo is good, but we still have a long way to go in terms of both capex and opex reduction. Yeah. So let's move on to some examples from our project portfolio. And as I mentioned, Grisat is a green hydrogen company. We work almost exclusively with electrolysis, and we try to combine that with our wind and solar competencies, because we see that this is an advantageous solution to be able to vertically integrate both the renewable energy production and the electrolysis. But nothing happens in isolation, so we kind of have to work with the whole value chain in order to realize these projects. And I'll show you how that works here. So I chose 3 projects that I think are interesting enough and different enough for you to get an idea of the different solutions and different scenarios that we work with. And these are all from Norway. And first up is Stord Hydrogen. It's a small pilot plant, which is grid connected, and it's in operation. So it started operation in May this year, and it can produce about 400 kilos of hydrogen per day. It is operated and majority owned by HYDS, Hydrogen Solutions, and Greenstat and Altec are co-owners. So we were part of designing and developing this project. So the hydrogen here is produced and supplied to the next door neighbor, which is the Sustainable Energy Catapult Center. And they test different fuel cells and different hydrogen engines that we've discussed for research purposes and for different clients in Norway. We can also supply compressed hydrogen to in containers, so in compressed form to well, basically any application, but generally maritime or construction energy or transport sector. So that's Stord Hydrogen, and it's in operation. It's it's working. So we're proud to talk about this. Then moving on to Glomfjord Hydrogen. Glomfjord is in the north part of Norway, and it's an industrial sort of area that has a very long history. And here we are planning a large-scale hydrogen plant with 20 megawatts of installed capacity. This will also be grid connected, and it's a project that's been in development since 2016, and it was founded by Greenstat with Nel, the electrolyzer company, and Meløy Energi, and we also have now Troms Kraft as part of the consortium. And this project was awarded 150 million kroner, so about $15 million in funding from the Norwegian government in 2022. And we are working now to reach a final investment decision, hopefully by the end of the year, but yeah, it's coming. We have a 40% working interest in this project, and we'll start hydrogen production in Q2 2025. So this project is a total investment of over $30 million. And the major components include, so the electrolyzer, which is 125 million NOK, so $12.5 million. We have the buildings and the land improvements, so about $5 million, and the installation and commissioning, which is also about $5 million. And the market for this project is 55% in the maritime sector. So that's the goal of the project, is to supply hydrogen for maritime transport. And then we have some contracts based on land transport or long-haul trucking, and some for industrial applications. And the oxygen in this project is going to be sold to a local industry for fertilizer production, a company called Yara. So this project is very interesting, and we have several projects that look like this. We actually have two other projects in the same size range with the same type of market that we're targeting. Finally, I want to talk about Kärlingland Energy Hub. So this is a little bit less mature, but it's a very cool project, and I think it's very applicable to India and Sri Lanka as well. So this is a gas station, and it's very close to where I live in Lillesand, with a climbing tower, as you can see in the background there. It's a tourist attraction. And what we are planning is to produce hydrogen locally through solar and wind that we will be installing on the lot. We'll also be grid connected to increase our renewable energy availability. So this gas station will then be able to supply both fossil fuels and green hydrogen, and also charging for EVs. So this project will it'll supply between 500 to 2,000 kilos of hydrogen per day, and we're currently developing a control system for the solution to be able to optimize the cost of the hydrogen that we will sell. And we're targeting a final investment decision next year. So we're currently in development, but it's a super interesting project, I think. Okay, that's all I had. Before I say goodbye, I wanted to just mention that we have next week a symposium in Sri Lanka, Green Hydrogen Symposium. I invite you all to come there if you are in Colombo. And also, I wanted to just tell you that there is another webinar on November 28th about a ship that's been retrofitted with fuel cells. And my good colleague Sabina will be talking about this project here. So it's free and open for everyone, and it will happen in English. So I hope you can join us there as well. Thank you.
Thank you. Thank you, Uda Maria. Sibi, you can moderate the Q&A session now. So I think Jonathan is here as well. Jonathan, Velag, Julia. So I think we could start with the Q&A session. Sibi, if you could moderate it.
Yeah, sure. Yeah, so we have very interesting questions in the chat box. Because of the limited time, we may not be able to answer all the questions. I will leave my email ID here in the chat box, and if your questions are not answered, you can write to me and we'll get you the answers. So I'm not addressing to any experts. It's a very common, like any experts from HBL and Greenstat can answer these questions. First question is, how much is the efficiency when we re-extract hydrogen from ammonia after transportation to the destination?
Jonathan, are you there?
Yes. Do you mean how much energy you use, or what do you mean? When you crack ammonia back to hydrogen and nitrogen?
Yeah, so I think he's expecting you to answer like what is the efficiency of converting hydrogen to ammonia.
Other ammonia to
hydrogen from ammonia back.
Okay, so probably between 70 to 80%.
Okay.
Okay. Next question is, why can't we use stainless steel coated with nickel in the bipolar plates for alkaline electrolysis? Stainless steel provides corrosion resistance and hydrogen embrittlement resistance, and nickel coating helps in the movement of electrons from electrolyte to electrodes. Since platinum, iridium, etc. are rare earth metals and are costlier, why not to try with stainless steel?
For the bipolar plate, you can use whatever material you want with some limitations. But the question you ask is the coating. So what you normally do when you make a bipolar plate is that you make it with the metal that has high conductivity, but then in the interface between the bipolar plate and the actual fuel cell or electrolyzer, you need some coating. And there are many metals you can use. So what you need to be sure of is, as he writes, for instance, for alkaline, you will have a very high pH, which means that you can have some type of alkaline corrosion, and the same for PEM, where you will have a lot of low pH, and then you need to be careful with the corrosion from the acid. And then another question is the formation of oxide layer. So let's say that you use nickel, you risk of getting nickel oxide in some cases, and this will typically, when you get oxides, you will reduce your conductivity. So in all the cases where you use a metal coating, you have to make sure that the metal don't give oxides. So let's say, for instance, in PEM, you could use titanium. But then at some point you will get titanium oxide, which has a really, really poor conductivity. So it doesn't matter if the metal itself has good properties if you get the oxide. So I think that the problem with nickel might be the fact that you can get oxides, but the exact chemistry of this I need to check.
Yeah, so just adding to that question answer, I would like to answer that there are already companies working on the same thing that I'm aware of. So there is a lot of research going on with stainless steel coated nickel coated stainless steel for alkaline electrolysis, and that's a very good option. As Jonathan mentioned, there are some chemistry issues with that, but but it's still possible. There are many people trying to do that.
Yeah.
And next question is, why have you not considered using byproduct oxygen for sale as that will reduce the electrolysis cost and manufacturing hydrogen become cheaper.
So you do that. As Oda says, it's very typical to produce have your electrolyzer with, for instance, a fish farm or some oxygen-demanding industry. But if you look at it, the need for oxygen is not that big. So even though you can use some of it, you will never be able to use all of it. But a lot of these modern plants for hydrogen production, they try to also sell their oxygen. So this is being done already.
Yeah. From JSL, we have many questions, but I would take one or two from them. Current material which is being used for the storage and transportation of gaseous hydrogen. What are the materials used for the storage and transportation?
So you have different options. You can use actually a regular metal tank, aluminum, steel, whatever, and then in some cases when you use regular metals, you need to coat them with, for instance, a plastic liner to avoid the leakage of hydrogen into the metal, which can ensue embrittlement. So that is one option, but another option is to use composites, which are polymeric based material, either layer by layer composites. And so the problem is that you have a kind of a trade-off between what material you can use and the pressure you want to store your hydrogen at. So I had a discussion with a representative from Hexagon Purus, which produces these tanks, and he said that now it looks like 350 bar, it's the limit, because if you increase the pressure a lot, no matter what material you use, you need to have a severe thickness of your material, and then the weight of the tank becomes problematic. So it's a trade-off, because pressure requires stronger materials, makes the tanks heavier. If you have less pressure, then your tanks are lighter typically, but then you get less hydrogen in your tank.
And there are a lot of research going on metal hydrides as well for the past 20 years. So metal hydride is another way, in a way. Yeah.
Yeah, a lot of carbon-based materials.
Yeah.
Also, people are doing research. Next question is, what are general size of bipolar plates of electrolyzers, and how much does it changes with increase in the capacity of electrolyzers? So size of the bipolar plates.
Yeah, so what you're actually saying is that inside the, let's say, a PEM or fuel cell, you have this on your, it depends on your system, but I think that you can have bipolar plates that are really big depending on your capacity, but I don't have the exact number for large scale electrolyzers, but I can check while we go through the other questions.
As you say, it is in different sizes.
Yeah. Another is very general policy related question. Maybe Professor Dylan can take it. How do policy makers and industry stakeholders view the integration of hydrogen production with offshore wind power, and what policy frameworks are being implemented to support this synergy? Am I audible?
Yes, Sebi, to whom you have addressed it to?
I was thinking maybe Professor Dylan can answer, otherwise anyone else can answer.
Yes, Professor.
Perhaps I can answer.
Okay. Yes, Vlog is there.
Yeah, please.
Yeah, please, Vlog, that's your question, please.
Thank you. So this varies obviously a lot from country to country, but the rules and regulations for offshore production of hydrogen, at least for Norway, is not in place yet. So this is something that we are also working on in our research center. So for now, if you were to build a platform offshore with hydrogen production, you would probably be covered by, in Norway, you would probably be covered by the law of petroleum, because that is the closest regulation system that we have now. But it's quite clear that new laws and regulations are needed for this, because this is a new industry that is not the same as the petroleum industry. So this is not in place yet. But there's a lot of activity on it. And there's a lot of different countries that are working on it. So hopefully within the next few years, we'll see some more regulations in place.
Okay. Thanks, Professor Velu. Another question I would like to take is, have you got degradation information for electrolyzers?
Mr. Jonathan.
What type of information you want? Or
Basically, degradation levels.
yeah.
Yeah, maybe like about lifetime and degradation in general you can cover.
So I'm not at least for fuel cells. I think they imagine that you you exchange some parts of the fuel cell every 3 years, and it's typically the membrane electrode assembly. And I would imagine that it's the same for electrolyzer, that you need to do some yearly maintenance, but also in a 3-year period you should exchange the membrane once. But we didn't really get into this, but an electrolyzer and also a fuel cell has a lifetime which is dependent on how you run it. So a good example is a fuel cell that you have for stationary applications. It will run like with the constant load for its entire lifetime. Then that is situation one. But if you put the same fuel cell in a Toyota Mirai, for instance, then you can take the lifetime and you can divide it by 3. So it's really dependent on how you run it.
Yeah, sure. So a question to Oda. Do you produce hydrogen refueling station infrastructure? If so, do you get involved in integrating hydrogen production with dispensing?
So we don't produce the infrastructure, so the refueling stations. We only supply hydrogen to whomever needs it. But in that development, we might work with technology providers who do produce the refueling infrastructure. Yeah.
Thanks, Oda. Or methanol, depending on energy storage, fertilizer, etc.
Okay, are you asking between only ammonia and methanol, or are you like?
Yeah, so I think they compare maybe between ammonia and methanol, which one is the best carrier in terms of energy storage and using it in fertilizers and all?
Yeah, I mean, so as you know, ammonia is already used for fertilizers, and then, in my opinion, but please feel free to join in if you others want to say something. But ammonia is good in the sense that it's been used for a long time, not as a transport not for transport, but as a refrigerant. So there is a lot of technology development that has already been done for ammonia. And then the major concern right now is the toxicity for human life and sea. So there's a lot of there's a process ongoing how to deal with this, and at least in Norway, the maritime industry has made a handbook on how to handle ammonia at sea. If you can mitigate the fact that it can become quite dangerous at relatively low concentrations, I would say that ammonia, at least for deep sea shipping, and it's a viable energy carrier. And right now, because the problem with for instance, methanol is that it's based on fossil sources typically, right? So if you want to reduce the fossilness of your fuel, I would say ammonia.
Yeah. What about the conversion efficiency from ammonia and methanol?
Yeah, I'm not sure how these compare. I don't know the efficiency of how you take when you take hydrogen out of methanol. I don't know what it is.
Okay, fine. Yeah. How is the situation with trained skill sets availability? That's a very general question.
I think that is the first thing that was a question I like, because it concerns both Sri Lanka, India, and even Norway. So I think we have to work on it because we start from scratch actually, as far as hydrogen is concerned in Sri Lanka, for example. There are a lot of attendees from Sri Lanka. So that's what we have to work on. The universities have a responsibility there. We need vocational training, and we need university, courses on hydrogen. So skill development is the first thing we have to work on in Sri Lanka and India. So these type of courses are very important, and we must establish curriculums in hydrogen. That's another important thing. So even in Norway, it is something new. So this is as you all know, HUL is the only institution in Norway which has these type of courses now for industries. And we are one of the universities which started with hydrogen courses first in Norway. So in that sense, a lot of things have to be worked on: curricular development, vocational training, and as Belog pointed out, from hydrogen production to development of systems, the whole supply chain has to be developed. That is one thing. Regulatory work, that is another thing. So a lot of things have to be worked on.
Yeah.
Yeah, Professor Dharam, thank you for your very elaborate response. And India is also taking, a lot of action and steps, including IITs and engineering institution in India, to introduce such the courses. And because this is very, very big limitation, apart from the financial limitation, financial resource, the second most, the biggest problem what I see is the availability of the skilled resources. But thank you very much for your very elaborate and very good response. Thank you, Professor.
Yeah.
I have a question, Dr. Sibimuluk. I have a question.
Yeah, I will be taking your question, sir. I'm seeing it in the chat box. So would hydrogen be able to replace dependence on fossil fuel by 2050, or the world would be dependent on fossil fuel even by 2050?
I don't know. I think personally, I feel that there will be fossil fuel as well into 2050. But because Norway has an ambition to become 90 to 95% carbon free by 2050. But the other countries, China, for example, they have their ambitions to become carbon free in 2070, and India 2070. So yeah. So we don't know. But there is in the future carbon mix, of course, future energy technologies, of course, hydrogen is going to play a big role. At least up to 10%, I think it will be based on hydrogen. That's my personal opinion. And solar is going to lead the technology, I think. Solar, wind, and hydrogen, of course.
Yeah. I think there are a lot of personal opinions about this question. Yeah. So, Jonathan, there is one more question, then we will close the Q&A. What's the minimum size of bipolar plate?
Let's say that in this cell, the membrane area is maybe 2.5, 3 square centimeters, and you just need a bipolar plate that is a bit larger than your membrane. So you can just take your membrane area and add like maybe 20% of that area. So for instance, if your membrane is 5 by 5, that's 25 square centimeter, and then your bipolar plate, it's maybe 30 or 35 square centimeter.
Yeah. Thanks, Jonathan, for answering this question. Thanks to all of you who have answered. And I'm really sorry that we are not able to take all the questions right now. As I mentioned before, I will drop my email ID in the chat box. Please feel free to test your questions to me and we will get you the answers. So now we will move on to the next session. So we are having Mr. Rajan Vashney. He's presently taking up new initiatives at NTPC, the largest power company which is diversifying into related fields. He did his MTech from IIT Delhi. He has over 35 years of experience in the energy sector and has been doing innovations that have won many accolades. He spearheaded efforts for September 2020 notifications for hydrogen HCNG as permitted fuel in the Indian Motor Vehicle Act and safety standards for FCEVs. He is passionate about the environment and sustainability, and he has been a lead speaker at various national and international conferences. So far in our training sessions, we mostly covered about hydrogen production using electrolysis. So Rajan sir will be taking how hydrogen can be produced from waste and biomass. Over to you, sir.
Is my presentation coming visible?
No, sir.
Not as yet, please.
Okay, just wait a minute. Maybe it is. Are you seeing something like sharing something or something?
No, nothing at all.
Okay, just a second. I am getting a message. Your screen is loading.
Yeah, we can see your screen right now.
Now we can see it.
Okay, so basically, I would like to say that hydrogen, if we want to do it in a cost-effective manner, water electrolysis is not the only thing. There are cheaper methods, and if we say take an example of how much water will be required to generate, say, 5 MMT of hydrogen, which our target is there in the mission for internal consumption, and then up to 5 MMT more for exports. So billions of liters of water is required and tremendous amount of renewable energy is required because green hydrogen is the target. Our whole hydrogen usage is targeting GHG emission reduction, combating climate change. So if we produce so much electricity, use so much water, then maybe some of the greenhouse gas reduction objectives may not be met, or some issues may be there, some counter effects are there. So if we use waste towards production of hydrogen, or even if we do electrolysis, but we do certain innovations to reduce the GHG emission, to use the heat value of water. And this is the basic premise that is slightly different from what you have heard in your till now. And just to complement that, I am covering this area, which is mainly concentrating on hydrogen from waste and some other newer techniques. We all know that the GHG effects are very disturbing for India. Our top 15 cities out of top 20 world's polluted cities are there. Then if we don't use this opportunity, when India, Sri Lanka have a lot of development to take place in next 30, 40 years, 50 years, whatever we have done is hardly 10% of the capacities which we require later. So if we change our methods towards cleaner energy usage and cleaner production methods. So it is a great opportunity. Now, not only electricity, like fuel, transportation, and feedstocks, all have to be changed, because electricity contributes only 18% of the energy need. Even if you make it totally green, a lot of other things are still to be made green. But waste is such a thing that it is already accumulated in our landfill sites and across the world. And people are worried how to control it, how to eliminate it. And hydrogen presents a very good opportunity that I am covering now. And even we can use agroforestry or some Napier grass and other things which can be even grown in the areas which are not fertile or don't have much water also. Plus, if we use this biomass as well as the agro waste, the municipal solid waste, and animal dung, sludge, sewage sludge, poultry waste, agroforestry, there is tremendous amount of waste available and we have to use it. And we have seen that in Tokyo Olympics or China Winter Olympics and all further coming games also, that lot of hydrogen usage is there, and vehicles, cooking, heating, cooling, everything can be done. Electricity can be done through hydrogen. And burning waste or leaving it as it is not a alternative, because if you leave the waste as it is, it liberates methane, which is 84 times more potent than CO2 as a GHG gas. So we have to rather utilize that methane and convert it into hydrogen, or use it as a methane itself, but somehow use it and convert it to CO2, which is very much less potent, or even that capture that CO2 which gets produced and make it into other fuels by reacting with hydrogen produced by us. So we have to reimagine the waste as a resource, and do waste management in a proper manner so that we can get fuel out of it and other things out of it, useful things out of it. And we can control this. This slide shows that from the waste in the lowest rectangle, the methane is coming out, and we can always control it. Similarly, from agricultural things, we see that a lot of animals are used, a lot of methane is there. We can control it. We can use that methane. Various companies across the world are having different technologies, and some are having small plants, some are having big plants also. Like Pensaco, USA is having a small decentralized hydrogen production plant. TRI USA has a 500 TPD biomass processing plant, and it converts it into SAF. And it first converts it to syngas, then it can convert it to anything. SAF will be produced shortly, and hydrogen syngas can be used to make hydrogen easily. Then several other companies are there which I have listed. Then the advantage of this Pensaco process of pyrolysis is that it generates biochar. And if we use this biochar to increase mix it in the soil, we can really further suck more CO2 from the atmosphere. And the process is highly carbon negative. First, we have produced hydrogen, which is saving us a GHG emission. Then this biochar also, as a soil amendment, helps in absorbing carbon. And moreover, the soil fertility increases. So less amount of fertilizers are required. Fertilizers again require ammonia, and ammonia requires nitrogen and hydrogen. So there is a lot of synergy. If we use waste properly, we can reduce our energy requirements ultimately, and the requirement for using fertilizers and for production. Similarly, many companies are like H2 Industries having a 3 billion plant for converting 4 MMT of organic waste and plastics into hydrogen. Oman has a plant of H2 Industries which is for 1 MMT MSW input. They use integrated thermolysis. Then SGH2 has a plant with plasma gasification. Waste2H is again having a technology, and they have collaborated in India also with one company. Then Waste2HHO, this is like we are converting water into brown gas. This HHO is called brown gas. Instead of making hydrogen, which takes in a lot of electricity, here very little electricity is required and a lot more energy is produced. This is an example of a Indian company where glass is produced in Bharuch in Gujarat. They have reduced their natural gas consumption 14%, and the whatever addition they did very recently, they had done in around first quarter of this May only. Only 6 months have passed, and expected ROI is 24 months. Brown gas has a better combustion efficiency and aids more complete fuel consumption. So emissions are reduced. If we compare, like for 1 kilowatt hour of electricity, around 860 kilocalorie of heat, we are getting HHO, which is giving us 50,000 kilocalorie of corresponding fuel. They employed Spectrum International consultants to deliver this system, and the fuel saving was 15%, then smoke reduction 85%, sulfur dioxide reduction 70%. So we have to use technology in such a way that we reduce our fuel consumption and simultaneously reduce our emissions. When brown gas is consumed, it is like HHO, protium, like electron is taken into valence shell of oxygen from the hydrogen. It has 2 hydrogen atoms, so it becomes protons, and electron goes into a hydrogen shell. So this is like when it gets combined into hydrogen again, water again, a lot of energy is released. And with respect to electrolyzers, there is a lot of capex, opex, and in their CUF. If we use renewable electricity, which is available around only 20-30% time of the day. So lot more electrolyzer capacity can be saved if we use waste or use innovative techniques. And in electrolyzers also, new electrolyzers are coming up, like Advanced Ionics is having a Symbion electrolyzer, which will use 35 kilowatt hours of energy for hydrogen, 1 kg of hydrogen. That is 35 units of electricity for 1 kg of hydrogen. It is using a SOEC process, the same the Bloom is using, but Bloom is at a high temperature. This has a temperature of hardly 150 degrees centigrade. And so it requires lesser electricity also. This is the advantage here. And it doesn't use any platinum group metals. And mostly it is made of stainless steel and low cost materials. It doesn't use ceramic also. Similarly, IIT Bombay scientists have used external magnetism to reduce electricity consumption and thereby increasing the hydrogen production. Then Highstar and Semcon have collaborated to produce an electrolyzer which will be producing 150% of the electricity which Star is again producing. Then there are methods to use seawater or even sewage water. And AEM electrolyzers don't use platinum group metals. They can be easily made robust to use this water directly. Then So High Tech is a European company which is having a electrolyzer inbuilt in a big dish. This is a Swiss-based company, and they are building electrolyzers which are called big dish. And they have a system in which the CPV is, it is called concentrated PV, which converts electricity at very high temperature, but it has very high efficiency. So what they do is they just put hydrogen in one pipe, oxygen comes through second pipe, and the hydrogen is the main useful thing which is coming out after the electrolysis. The electrolyzer and CPV. CPV is converting that light into electricity, and hydrogen is just at the back of it. Electrolyzer is just at the back of it. Then the advantage is this system can be, they can use make a temperature through sun only, a reflection through mirrors in the big dish, and the temperature can go up to 1500 degrees centigrades. So what happens is we can use this temperature for direct photocatalytic splitting of water also to make hydrogen. And also this can be used for for other solar fuels also. Then we have CSP plus storage. This is called concentrating solar power plus molten salt storage. We use sun's heat to produce electricity ultimately. But what we do is we put these heliostats or mirrors, and receiver is there. These mirrors act as reflectors and reflect sunlight into the receiver, and a lot of heat is generated, maybe around 700 degrees centigrade or 500 degrees centigrade, depending on how much you design it and what is your heat transfer medium. If we use molten salt, we keep this temperature around 550 degrees centigrade and use a heat exchanger to transfer heat from the molten salt to the water, and water converts into steam and runs the turbine and gives us 24/7 renewable power, firm baseload power without any intermittency. So this electricity, if we use with electrolyzers, we can have electrolyzer utilization factor of 100%. So overall cost of hydrogen becomes 2/3. And these technologies can be used for carbon capture also, because if a coal-based thermal plant is there, it is generating CO2 24 hours. And if we use this renewable electricity to catch this hydrogen, we are much better off. Similarly, biofuels can be made through this 24/7 renewable electricity, firm electricity. Now, towards the utilization of waste, mainly I have given you only some typical examples. Now, basic processes you have already understood during the earlier presentations. Basically, you do, if it is wet waste or if it is a mixed waste, you just segregate wet waste out of it and do anaerobic digestion. Then you do steam methane reforming, or second process is methane pyrolysis, which I'll give you some examples also. Then instead of segregating, we can always take the mixed waste and use gasification to do the syngas. And then from syngas, we can make anything. It is a basic thing, and a lot of petroleum extraction can be saved. Then plasma gasification, we like I had shown one SGH2 company. Then pyrolysis, there's it's low temperature and partial oxygen presence. So we can pyrolyze the waste also. Then newer technologies based on microbial things are also coming up. This is a Forest Plasma lab which have a zero-emission company technology, which is again a plasma-based thing, and they produce syngas out of it, and from that we can segregate hydrogen through membranes. Then rise hydrogen is there. It converts plastic to hydrogen and graphene. So this is something like methane pyrolysis, and we are getting a very costly byproduct out of it, which is 5,000 rupees per kg. One company, Universal Matter, is already doing it. Another company, Levedian, in UK, is also doing it. Then there is other methods also. This is a tri-generation fuel cell. It gets biogas from the anaerobic digestion of the wet waste and converts it into electricity, hydrogen, and water. They have a patented process. This is an example of the plant. Then many big companies are also coming up fast, and this Toyota has a plan to convert waste to hydrogen by 2025. Then this is another company which has a hybrid pyrolysis gasification technology, and they call it Ecomotive. They do high density gasification, and they have an integrated system to segregate hydrogen out of the syngas produced, and they can do it from 500 kg per day capacity to even 5,000 kg per day through this platform only. And the advantages in the table, we can see that the net water usage is 1/3. Net electricity consumption is 1/5 or 1/6 even. And all this makes it hydrogen cost below $1. Then this is a RGH2 Austrian company which directly converts biogas into hydrogen through dry reforming, not steam methane reforming. No water is used. Then this anaerobic digestion. Then basic thing is with the waste, we can do the decentralized hydrogen production. And the advantage is that transportation cost is reduced, the storage cost is reduced. If we can produce hydrogen near the point of use and in the right quantities. Many vendors are using SMR. They have a small SMR. This Biotech USA has it, High Gear has it, and many other companies are having such small systems. They can produce hydrogen in your backyard or on your roof also. Then if we can, in that, we have to capture hydrogen if we use SMR. Sorry, we have to capture CO2 also to reduce the CO2 production emission. That is much better. Otherwise, with the 1 kg of hydrogen production, there is about 9 kg of CO2 production. Although that is a biogenic production, because the biomass which took in that CO2 during its growth in last, say, 3-4 months or 3-4 years, whatever ages, that same CO2 is getting liberated. So net CO2 is same, but we can also capture that, but that requires energy. And there is a method of not requiring even capture of CO2 and making it the whole process highly carbon negative. This is called methane pyrolysis or methane splitting. Here, hydrogen and solid carbon is produced. Solid carbon can be in the form of carbon black, which is used in tires, plastics, or in dyes. It can be in carbon nanotubes, it can be in graphene form, it can be in fullerene form, it can be in carbon nano-union form, or biochar, or artificial diamond, or graphite, which is used in electrodes also, in pencil lead also. So many things which require petroleum extraction or coal extraction, they can be reduced, and from waste we can have hydrogen also, and we can have, without any CO2 capture expenditure, carbon in solid form, and which is very useful if we use, like we have seen in the earlier example, if we use it as biochar for soil abandonment, we can reduce fertilizer requirement and also make soil more capable of absorbing carbon from the atmosphere. Similarly, these carbon nanotubes, graphite, graphene, all these things, some of these are very costly. Like graphene is costing around 5,000 rupees per kg and is a very versatile product. Fullerene costs around 10,000 rupees per kg. So if we sell these products, we can get hydrogen nearly free of cost. So $1 is nothing, we can have nearly free. Big companies are already doing it. Plasma methane pyrolysis is being done by this company, and they are having Monolith USA. They are having second plant also, making it commercial plant. This is Hazer, Australia. They have recently commissioned their plant. They have a slightly different technology, but it is also methane pyrolysis. Then some other companies are doing it. Then this Levidian, which I earlier said, this is having methane pyrolysis. They call it loop, and they convert methane. It can be from any source, but if it is from biomethane, like from waste, it is much more better. And they convert it into graphene and hydrogen. This is an Indian company, Paganism Innovations. They have a Rudra reactor, which converts methane into carbon black and hydrogen. Then there are other companies like IOC and IASC Bangalore are scaling up a technology for biomass gasification. Sentient Labs, which is a unit of KPIT research, they are also working on it. Thermex is working on it. Institute for Plasma Research has developed gasification technology. And if we see that wet waste to biomethane and then biomethane to hydrogen, it gives us hydrogen at very competitive rates, which is even less than 100 rupees per kg. It depends on how much carbon credits you can earn, because carbon credits you can earn in the process, but what is the rate of the carbon credit, one credit? At times it becomes very high. So we have to accumulate the carbon credits and sell it when the rate is high. Like if we use electrolysis and the PV and other source of renewable energy, lot of land is required, lot of energy is required, lot of water is required, lot of materials, costly materials, nickel, platinum, iridium, etc. are required. So if we go through this route, waste to hydrogen, we can have it more GHG emission free, and rather at times carbon negative also, and at a cheaper cost, simultaneously protecting our soil, water, etc. And this microbial route, this is a very good route, but it is in TRL 4-5 levels, 6 level maximum. Different companies are doing it. Here you don't need even electricity, and the microbes themselves produce those enzymes, and these enzymes disintegrate waste into useful products, which can be hydrogen, methane, methanol, ethanol, carbonates, bicarbonates, sulfates. And some of the products can be converted to such a form that which can be sold at very high rate. Like if we make ethylene glycol and terephthalate acid, then make sodium terephthalate. Sodium terephthalate sells at more than 50,000 rupees per kg. So again, although process is cheap, reactor is cheap, microbes are themselves replicating. So all these costs are very cheap, and moreover, the byproducts can be very costly. So we can produce hydrogen at a very low rate and reduce consumption or not require even these platinum group metals or rare earths, etc., which are in any case not available in India and Sri Lanka, and otherwise they would have to be imported. And moreover, this hydrogen technologies, as compared to BEV battery electric technologies, use very little materials of costly things like platinum group and rare earths. If we see in the upper three slides, three halves, this is there. And if we use hydrogen, then for electrolysis and even for fuel cells, we require very little quantity of these materials. In India also, hydrogen vehicles have been launched, and the notifications, I got these notifications done for FCEV safety and type test approval. This is GSR 579E, and HCNG and hydrogen as a permitted fuel 585E. And the best part is these cars run in 5 kg 650 kilometers. So if hydrogen is say 100 rupees per kg, the running cost is hardly 1 rupee per kg. This is Gadkari ji launched on 16 March, Toyota Mirai. And even the HCNG, hydrogen blended in CNG, reduces pollution. When that notification was done on 25th September 2020, from 1st October 2020, 50 buses were run on HCNG DTC buses in Delhi. And the pollution emissions were very much lower. CO was reduced 70%. Total hydrocarbon content was reduced 70%. And the efficiency of HCNG is 5% more. And SPM level decreases tremendously because hydrogen produces ultimately steam, and that steam doesn't allow this smaller particles to fly out. Then this hydrogen can be used for co-firing in the power plants of coal fire nature, or even it can be ammonia co-firing. So all this can reduce pollution even if we have to use coal. But what I have shown you is CSP plus molten salt storage that can replace very well baseload power from coal also. Then some of the
Excuse
plants
me,
are
sir.
replaced.
I'm
Yeah.
really sorry to interrupt you. Would you able to wind up in another 2 minutes?
Yes, yes.
Okay, thank you.
So some of the policy interventions are required, like carbon intensity should be measured instead of saying as green hydrogen or whatever. Like we have defined carbon intensity of green hydrogen in India as 2 kg CO2 equivalent of non-biogenic resources per kg of hydrogen produced. Similarly, pilots should be funded, and then more companies will come up and scale up these things, and whole hydrogen economy will develop in next 2, 3, 4 years. Then carbon market regulation should be brought in fast. They indirectly help in subsidizing the cost of this hydrogen production, and ultimately leads to penalty to the GHG emission industries. Then policies supporting decentralized waste to hydrogen production should be promulgated, notified, and this reduces the transportation cost of hydrogen also, and it can be produced near the vehicle or near the tractor, and anywhere waste is available wherever the population is there. And just like RE, banking of biomethane should also be there, and even injection anywhere, just like electricity you inject in the grid, you draw it from anywhere. Similar policy should be there for this. Then bold, stable tax incentives should be there. Demand creation towards using green hydrogen should be there. What we have seen is the production linked incentives for electrolyzers or green hydrogen production directly, but there is no obligatory demand or some other methods to incentivizing the usage of that hydrogen. Similarly, PLI incentives for SMR and methane splitting, methane pyrolyzers should be there. So these will be more cheaper and easily available. Then ecosystem development for better coordination of academia, startups, research, industry, and financing should be easier. Like this is also an venue where we are targeting students and companies are there to help. Researchers should get credits for industrial participation, not only for writing papers. Then credit-worthy aggregators like SECI should come out with a demand aggregation. Then hydrogen from waste is like it can be stored, and also waste can be easily stored. And when needed, hydrogen can be produced. Major components are locally manufactured, lower capital investment is there, decentralized hydrogen production helps in cutting down the transportation cost. Rural microgrids, rural electrification can be done easily. So it is a key driver towards energy and environment, grid stability, and it is much greener than so-called green hydrogen and addresses directly or indirectly various SDG goals. So in conclusion, I can say that waste to hydrogen is greener than green. Green hydrogen is a multi-decade opportunity. Green hydrogen can integrate RE sustainably and thus provide energy across sectors. Various sectors can be decarbonized. Moreover, additional benefits become cleaner environment, methane flaring is avoided, waste treatment happens, cleaner energy is there, freeing of prime lands, which is locked up by landfills is there, more jobs, lesser migration, even in rural areas, we can have such industries. Lesser imports will be there. India imports so much fuels, and we would be in a position to export hydrogen and other low carbon products, steel, ammonia, etc. So it is a taking care of planet, people, and prosperity. It is 100% profitable way to do it. So it is a win-win for all. Thank you. I'm available for questions.
Maybe I can take one question if anyone has any questions related to what Sir has shared. Okay, I'm not seeing any questions. Thank you so much, sir, for introducing us to new technologies and routes for producing hydrogen that are more economical than electrolysis. And I forgot to mention in my introduction that he is the Deputy General Manager at NTPC. We will really thank you and we really appreciate with us. Yeah.
But let me state that whatever I have said, it doesn't indicate any company policy or anything. I have done my research and I have told my experiences.
Yeah. Thank you, sir. Right now, we are going to wind up the session. I would like to invite Mr. Umesh Sahadev. He is the Chief Convener of the Center of Excellence in Green Hydrogen. Sir, I invite you for your concluding remarks and vote of thanks.
Thank you, Sebi. Ladies and gentlemen, thank you for your participation in this. I will have a very important announcement after my small address, and then it will be of useful to everybody who is participating here. Today, as we reach the culmination of the first online learning session, Hydrogen for Decision Maker, which is a collaborative effort between HVL University, Greenstat, and PHDCCI Center of Excellence, it brings me immense joy to convey my heartfelt appreciation to HVL University and extend my profound gratitude to Professor Dalyan, whose exceptional coordination has been the linchpin of this entire program. Professor Dalyan's dedication has bridged geographical boundaries connecting Norway, India, and Sri Lanka to curate and initiate these enriching hydrogen courses under the PhD Center of Excellence and for green hydrogen. I would like to extend my deepest thanks to Dr. Vlog and Dr. Jonathan, Dr. Yulia, Professor Dalyan for their invaluable teaching contribution to this program. And what I will, they're actually insightful lectures and presentation on the hydrogen value chain and innovation have been nothing short of enlightening. They have provided us with a profound understanding of the intricate aspects of hydrogen technology and its vast potential and what lies in future. Our gratitude to Dr. Oda Mari from Greenstat for our instrumental role in coordinating this event between Greenstat, HVL, and PhD Center of Excellence, and our very useful techno-commercial session with useful Greenstat commercial and project development models. Thanks to Mr. Rajan Vashney for NTPC for his presentation on cost-effective green hydrogen product for greenhouse gas reductions using heat value, biomass, and number of other innovative technologies worldwide, researched by him. And then I would like to thank and acknowledge Dr. J.P. Gupta, whose visionary leadership has set the direction for the Center of Excellence. Your unwavering commitment, sir, to promoting knowledge and innovation in our field is truly commendable, and it's reflected in initiatives like this one. Then I take this opportunity to extend my heartfelt gratitude to our PhD team, particularly Ms. Kanchan Jutsi, Director of PHDCCI, who has been a pivotal figure in leading and coordinating our Environment Committee and the Center of Excellence activities. Her unwavering guidance and support has been of great value to create this type of event. And a very special mention goes to Dr. Sibi, Joint Secretary at PhD Center of Excellence, for her dedicated efforts in coordinating and moderating the event from the very outset, representing the PHDCCI's role. Her contribution has been invaluable in ensuring the success of this endeavor. In conclusion, I believe that the knowledge and insight we have gained during this online learning session will serve as a solid foundation for our future endeavors in the hydrogen learning program at PhD Center of Excellence. Finally, I want to express my gratitude to all the participants from India and our friends in Sri Lanka. Your active participation and valuable work towards a world free from carbon emission through the transition to hydrogen. Thank you for being part of this important journey. Now, a small information I would like to share with you. In very near future, in collaboration with HVL University and Greenstat, as Dr. Jonathan mentioned, we shall come out with our plans to unveil a comprehensive learning calendar for the entire year of 2024. This calendar will feature a wide array of courses, including physical, hybrid, and online options, covering all aspects of the hydrogen field, sustainability and decarbonization, as well as carbon markets. Our objective with this initiative is to empower participants from Sri Lanka, India, Nepal, Bangladesh, enabling them to meticulously plan their educational journeys to meet their specific learning needs and aspirations. Participants can leave their emails for us to convey these programs and all. Those what we have with us, we'll definitely share with them. And thank you very much. Thank you very much, Dr. Dalyan.
Thank you.
For
Thank you.
conducting this.
Thank you.
Thank you,
Thank you very much. Thank you. Thank you. Thank you, Ms. G. Thank you, CB. Thank you for all you who attended this course. We'll meet all of you maybe in physical means next time. We'll see.
Yeah, very soon.
We'll see how it goes.
Thank you very much.
Thank you very much. Thank you. Thank
Okay,
you all.
CB, you can conclude now the session.
Thank you.
Yeah, I have a question. Like few participants were asking about whether the presentation can be shared or recording can be shared. So, Professor Dailam, what do you say about
Yeah, we can do that, but I had a small issue with my recording unit, but I saw that Tulasi, one of these, Miss Tulasi, I think she was recording as well. So I hope that she could send it to us. So I have anyhow the first part of the recording, so we can share it. We'll see how we do that. So we can do that. We'll see that.
Yeah, Dr. Dalan, Professor, I think all the presentation can be sent to CB and she will coordinate the whole thing, please.
Yeah, we'll do that. We'll do that through CB. Thank you.
Thank you very much, sir.
Thank you very much. Thank you very much. Thank you very much.
Thank
you.
Thank you all for joining.
Thank you. Bye bye. Bye bye. Bye bye. Bye bye. Bye bye. Bye bye.
Bye.
Bye bye.